happy to welcome Chris Greer. He's getting to come back to his roots because he actually did his undergraduate here at Northwestern in physics. After that, he spent a long time in astrophysics research, did his PhD at the University of Chicago, right next door, and then went to do a postdoc at the University of Arizona. And through his career in astrophysics research, Chris worked on really cool projects like the Event Horizon Telescope, which is giving us the closest look that we really can at the horizon of a black hole. And he's done lots of work in innovating kind of data collection techniques, processing electronics, and developing software for many different telescope projects. But in 2015, Chris moved from astrophysics research to data analytics at KPMG, which is a name that I'm sure a lot of people have heard of before. So without spoiling the show, I'll let Chris kind of take it away and tell you the rest about data analytics and machine learning from a physicist's perspective.
Hi. So I originally pitched this to a grad school friend of mine who's John Everett, who works in Sierra. And the idea was that when I did this a year ago and jumped ship, so to speak, there was really no blueprint for it. Like people, at least in my experience from astronomy, when they leave the field, they sort of get mourned, like maybe they've died or something. So there wasn't really like, how to find your next postdoc or how to, go about doing the tenure track faculty search type of thing was very well evidenced. But none of my mentors, who were all physics faculty or astronomy faculty, had ever had an industry job. So there was really no sort of idea on how to do that. So I initially pitched this as sort of like reverse public outreach to help people in physics department who may want to leave academia after their PhD or postdoc, and sort of give an overview of what it's like to actually do that. And then I got hooked up with Mike and Hareka to do the machine learning portion of it. So half of this talk is actually going to be about basically the nuts and bolts of like what to expect when you're leaving academia. And then half of it is going to be kind of some of the stuff that me and my group at KPMG have been up to since I joined last year. So first, there's a warning no. So how many people are in the physics and astronomy department or are physicists? Okay, so maybe like a fifth of you. So this is an XKCD comic about physicists, and it's pretty representative based on my experience. And so the physicist is talking to someone and says, "You're trying to predict behavior of generic complicated system. Well, just model it as a simple object, and then add some secondary terms for complications I just thought about." And so, if a physicist could, and the punchline is, so why does your field need a whole journal anyway? So, if everything's basically a simple harmonic oscillator to a physicist. And so, this is my biased perspective, and I'm sure, especially if you're in an engineering department, your department may have closer ties to industry. So bear with me a little bit while I give sort of the nuts and bolts of my experience, and then I'll get into maybe some of the machine learning stuff here in the second half of the talk. And also, I'm amenable to questions. When I practiced this, I ran about 50 minutes, so we have about 5 or 10 minutes for questions. So if you want to ask something that's unclear, or just hang on till the end. So this is a plot from my thesis. And so my background is in academic astrophysics, and I didn't put any expository stuff, but one of the main results of my thesis is I measured this number to be 0.28. And the whole point is that no one in industry cares. By default, they think you're coming at something with a PhD, and a PhD is kind of mysterious. And so it's your job, when you're making the switch to industry, to sort of make people care. What is this? Well, this is parameters of a galaxy cluster scaling relation, which allow us to infer the properties of the dark matter within it, and therefore sort of cosmological parameters of the universe and that sort of thing. And being able to take a really complicated idea that someone may care about or may not care about and break it down for them is an essential skill here. And so a lot of what I ended up doing in this transition is exactly that. Because very often in industry, the goal, I think, is to get, I'm still learning this, but the goal is to have people give you money. And often the people who have the money aren't technical experts in machine learning or whatever. And so it's your job to make them care and make them understand. So here's a picture of me. This is what I did. So that's me. This is the South Pole telescope at the South Pole. It's a 10-meter radio telescope, and this little purple canister, it's like more of like a fuchsia, is our camera, and we put this camera in this telescope to join it with the Event Horizon telescope, which is a worldwide network of radio telescopes. And the idea is that by having telescopes all over the Earth, you can simulate having a telescope that's the size of the Earth and thus take pictures of something that's very small, like a black hole. And I put this up here to say that my experience with machine learning and my experience with what could, I guess, broadly be called data science was relatively minimal. Like, things like random forests and AdaBoost and whatever, what have you, were sort of getting, making their way into astronomy, especially in fields with like large surveys like LSST and LIGO from this Ideas Fellowship. But in practice, I was as much of a software engineer and an electrical engineer as I was a data scientist. So I had a bit of a challenge to come into the industry, but it wasn't really that hard to make the connection. A lot of what you do in data scientists, as a data scientist, is you sort of sit down and someone comes and says, here's a pile of data. If you're lucky, they know what question they want you to answer. If it's more typical, they don't even really know what question it is they want you to answer. And so the skills that you learn in academia, where you're working on some hard research problem that's extremely vague, and you're going to measure this number at 0.28. We only decided on that number several years after we'd started, kind of thing. So the skills that you learn, even if you're not actively using R or scikit-learn or something, are very, very transferable. So I just put this up. This is the last sort of data that I collected before jumping ship. So this is a famous astronomical object. So can anyone want to hazard a guess as to what it is? This was taken with the South Pole telescope in our camera. If it helps, the wavelength is, I don't know, 1.3 millimeters. Anyone? I don't know. It's kind of crescent shaped, so over here it's much brighter than it is over here. So yeah, last night was a really good example of it at some time. So all those years of work, and I took a picture of the moon. But the data science connection is that I was the one who wrote sort of the back-end pipeline that took this data, its voltages across a diode in an instrument, but it has to be calibrated, it has to be shipped around and moved, and all of these sort of software engineering principles informed by years of years of subject matter expertise are exactly what data science is. So this is like a really nuts and bolts of like how long it actually took me to get a job once you're deciding to leave academia. So back in ancient prehistory, I actually quit graduate school in the middle and went to work in the industry for 6 months. This was the first time, graduate school has its ups and downs, right? And so does anything in academia. So in one of those down periods, I thought I was really down, so I decided maybe a change of scenery was nice. And so I actually went to work in the industry for 6 months. Decided the down wasn't quite so bad, so I came back and finished my PhD. The other thing that you're doing right now, which is attending talks like this to start understanding the industry, is a good idea. And the thing that really surprised me most was getting involved with public outreach. I did it because I figured the government is paying for my research, and there's no immediate application for taking pictures of black holes. So it was kind of like a moral imperative for me to get out there and start talking about my research. But in practice, what happens is every job interview I had turned out to be a public outreach opportunity. When the interviewer sits down and says, tell me about yourself or tell me what you worked on, they didn't want to read my latest paper. What they wanted is a 30-second introduction to what I was doing and how it related to the job I was interviewing for. And so that was something, just talking about it with like your mom or like lay people is something that you can never do enough of too soon. In earnest, I really started applying to industry jobs sort of in June 2015, and had an offer by August, so it's about 2 months. But there was about a year of preparation in here, and so I'll talk a little bit about that. In practice, I didn't know how to do this, so I just used 3 different sources of job listings and just applied to about 300 jobs. And I ended up getting probably about 5 or 10 offers based on following things through all the way to the end. But by far, so it's very easy to apply to a lot of jobs. So 300 didn't seem like a lot, like it would be for academia. But in practice, because it's so easy to apply, you'll often hear nothing back. So the null hypothesis on this sort of test is that when you send out a resume, nothing will ever come back to you. And I was also a little bit worried, I guess, and so that whenever I went to a talk like this, it was like, leverage your network, talk to your network, talk to people who you know who are in industry. And I basically knew a bunch of physicists who had never been in industry. And it turns out my network wasn't all that helpful. They were there. They were like cheerleading me because they wanted to also get jobs in industry sort of afterwards. And I knew some people who had left academia to become, industry data scientists. And they were sort of helpful, but not one of them, I didn't get a single interview based on someone I knew previously. And so if you have a lousy network and all of your networks are people that you know in graduate school or undergrad or whatever, it's not the end of the world. And so the other thing that is like, I didn't keep statistics, and so this is a data science talk, but cover letters, at least when I was younger and learning how to apply to jobs like in school and stuff, not that I ever did it, was that a cover letter is almost as important as your resume. I don't think that's necessarily true anymore. I think having some sort of cover letter, like, marginally increased the response rate for resumes, but like whether it was super detailed or just kind of a perfunctory sort of thing, didn't really seem to make that much of a difference. And again, that's something that I noticed, but it may not be general. And so I'm here in Northwestern again because KPMG is doing campus recruiting with the Masters of Science in Data and Analytics program. Is anyone in that here? Okay, so no one. That's so good. I'm not talking, I won't have to repeat myself. But like when I first started applying to jobs, recruiters would call me, and I had no idea what a recruiter was. And so that person whose job it is to find people like you and provide them as workers for people who actually post the job. I wasn't sure how to talk to them at first. They know words like linear regression and Hadoop and stuff like that, but the real sort of detailed understanding of what does a distributed file system look like, or how does Apache Spark work, that's not what their job is, and so they're not technical experts. And so typically when you talk to your recruiter, they're actually on your side because they want you to get hired because that's how they're evaluated. Their job is to find qualified candidates, and it's like people like me now who are in the department that you're trying to apply for that only want the best candidates. So the recruiter is actually sort of your ally. And so typically after you send off a resume, within a few days, if you're going to get a response, you'll get a response from a recruiter. There'll typically be a half-hour call of like sort of an initial screen that says, this job requires 80% travel or whatever. And you say, well, I can't travel at all. So then they do that sort of initial screen sort of stuff. Then it's typically a series of phone interviews, like technical ones. And so the technical interview was a little weird. It was not something that I had done before, but I'll touch on that in a minute. But they're often like half-hour, 45 minutes things, and it's like a successive weeding out process. And they're not hard, per se. It's just something that you should be prepared for. Finally, there's an in-person interview. And again, for data science, they're often more technical. So for KPMG, we actually have you do a presentation on something. I did it on my thesis research because it had some data analysis involved in it. And again, the goal, no one cares in KPMG except for me, cares about galaxy clusters. But the point is, so we had a high energy physicist come give a talk, and he worked on the LHC. And he was working on trying to identify the progenitors of jets that they were observing. And it got into the weeds so quickly that I was the only person in the room that had any idea what he was talking about. And I'm just an astronomer, so like he basically lost everyone. So the idea is to see if you can take a complicated idea and explain it very, to someone who's not an expert in the way that they would care. And then you get an offer, hopefully, and for a given job, like the whole process will take about a month or two.
How receptive is the audience to, like, how curious are they about learning about galaxy clusters versus, well, how does this move our business forward?
So I found that in my talk, which was about galaxy clusters, they were super interested in the CMB, the cosmic microwave background. And I got a lot of questions about that. And those are the presentations are kind of fun, honestly, for exactly the reason that they don't pertain to business. And, but it's sort of up to you to kind of make them care. Like, I think the cosmic microwave background sort of sells itself. It's like the baby picture of the universe, kind of, this is the lumps are what grow into the planets and galaxies and stuff. But, I think, LHC jets are kind of cool too. You're like, incredible energy smashing particles together. But, no one cared about this other guy's talk, and that was purely on his presentation. So, anyway, hopefully to find the right job, like any one job takes about a month, but to find the right can take several months, so, plan accordingly. I used this particular book. This was recommended to me. So a technical interview, you only have like 45 minutes to determine like whether or not you're competent or not. So it's really hard, actually. It's kind of artificial. And so you guys have been working on your research for, in some cases like a decade or more. You can't distill that down into like a 30-minute interview. And so there's several books out here which are, data science really borrows heavily from software engineering in this particular regard, where they'll ask you questions like, you have a string, a text string and some code, write some pseudocode or write some code in Java or whatever to reverse it. And then they'll ask you other questions. And then so you need to ask, and the idea is to see that you work through a problem. So for example, in C, a string is like a null terminated byte array. And so what you have to do there is slightly different than you would have to do in Python, for example. And so they want to see you like make assumptions, talk through the problem and go through it. But the point is that it's really artificial. And if you're like me, who's in physics, I had never encountered, for example, a linked list or a tree or any of these common computer science data types. And because it's so artificial, this is what they come back to. And so it behooves you to both like learn what those are and also get in practice of working through these problems on a whiteboard, because typically that's either you're going to be doing it in person on the whiteboard, or you'll be doing it something like on a web program. I forget the name of it, but it's like pair coding, where you're both sort of sharing a screen and you have to type it through. So for example, a question I was asked by a consulting firm, data science consulting firm, was, I'm thinking of a number. I won't tell you what it is, but I'll give you a function that says whether you're higher, lower, or correct. Can you design an algorithm that figures out what the number is? And so, it's pretty simple. You set the bounds around the number because you don't know what the bounds are, and then you bisect the range. But then you need to ask, it's a lot harder if that number's a float rather than an int, and then then it opens up to questions like what's the time complexity for this, and so on. And so they tend to branch out a little bit, but it's worth at least practicing this a few times. And like I said earlier, you don't need to be like a machine learning expert, but you should know the basics. And so by the basics, I mean I went through the videos in the Udacity Intro to Machine Learning course, and this 3-hour video by Jake Vanderplas, who's an astronomer, I think, in Washington now, talking about how to use scikit-learn. Time well spent. So if you're not like, if your thesis research doesn't involve like, deep learning, neural network stuff, don't fret. Mine didn't. And then academics also get some specific questions. The first one is obviously, tell me about your research. And they obviously, like I said, they don't really care. They want you to like make it interesting for them or tie it back to the job interview. And this should be like 30 seconds at most. And then they're going to say, wow, you studied this awesome thing. Why do you want to come work for an accounting firm? And you could say, well, because in academia, the hours are awful and the pay is low and you have no job security beyond your next expiration of your postdoc or whatever. That's a bad answer. They want to make sure, you want to be exposed to a wide range of problems that maybe a consulting firm would provide you, or you want to, translate your skills into work on healthcare if you're talking to like a hospital chain or something like that. And finally, this is the one that I found borderline offensive, which was this image that academics sit around in like tweed coats with like leather arm patches and smoke pipes all day. And like, now it's 3:30, maybe I'll go do some work now. Can you keep up with the fast-paced business world? And you don't want to say, like, seriously, like, have you ever met a physicist or someone? But in reality, I work less now than I did as a postdoc. And so you just need to sort of educate your interviewer. But this question came up over and over again about how, hard businesses, and I'm still even sort of combating it today at KPMG. There's, this perception that academics, they take too long to focus on the exact correct problem, and when business requires you to think on your feet and decide what's best, and don't have perfect be the enemy of good enough. So these are 3 things that kept coming up in my interview, so it's probably worth thinking of answers. And I'm going to skip most of these slides, but I think the point what I wanted to make on this slide was that I was not terribly discriminatory about where I applied. I decided, I think, rather late that what I was going to do with my life after my postdoc ended. And I wasn't too picky, partially because I was afraid. And so what I want to combat here is that sort of fear that there is no life after academia. But there's like a lot of jobs right now, and if you can program and are good at doing math and can think through a statistical problem, you're going to get hired somewhere. So you can afford to be a little discriminatory about what you want. And it's sort of probably worth thinking about what kind of company, what kind of problems, and so on that you would like to do. And job responsibilities vary widely too. Like data science, for one, I really don't like that term. It sounds kind of made up, and sort of short of string theory, I think most science actually uses data. And so, what data science is incredibly broad field. And so if you're interested in doing like financial risk modeling, it's almost a completely different job if you're interested in doing sort of natural language processing stuff. And so if you don't know what you want to do, you maybe want to target a place where you get to work on a lot of different things. But if you have a very specific interest, it's worth, following that through. You don't have to be desperate. And so the sort of takeaway at the end of this first half of the talk is, I guess my wife put it best, is, academia is great, and if you want to be a professor at an R1 institution, more power to you, and incorporate machine learning in your research, great. But having that be the end and only goal for PhD education, I think, is a disservice to people doing the PhD education. But leaving academia isn't the cure for everything that else in grad school, just as, leaving academia is not the end of the world. So my wife put it this way: you still get aggravated, you just seem to get aggravated about different things now. And so it's slightly different. But it's, there are some things that are much better about not being in academia, and there's some things I frankly miss. The one takeaway that I've noticed is that the soft skills needed to, by soft skills I mean like negotiation or giving these talks, not your technical programming ability or your math, your ability to like solve like weird integrals. But the soft skills necessary to be successful as an academic, there's much less overlap than the technical skills, as with what will make you successful in industry. So I'm still working on that point. So that's the crash course in how to find a job. The overall, or at least how I found a job, the overall message is like, don't worry, I guess, don't panic. And but there's a lot of different, it's a new language I had to learn. And so if you have questions about it, I'm happy to talk about it to you later. And in particular, you should come work for KPMG. To further enhance that, I'll talk a little bit about the projects that we work on. And so KPMG are all names, and I can never remember what they are. And it's like Kleinveld, Marwick, Pete, and Girdler or something like that. And they're all like dudes from like the 1800s who had accounting firms. And initially they were separate, and throughout the years they've essentially merged. And for a while, KPMG in the US was Pete Marwick and Company or something like that. And they've been KPMG since sort of like the early 2000s. We are one of what's known as the Big Four in accounting and audit firms, with like Ernst & Young, Deloitte, and one that I can't remember. And so by far the bulk of the employees at KPMG are like accountants, and they focus on things like, you know, how to move your headquarters to another country and save your company billions of dollars on taxes, or alternatively, coming in and looking at your books and making sure that you're not the next Enron. So if you're too young, Enron was a company that basically like had magic accounting books and was effectively losing money just by setting it on fire, and everyone thought it was great. And so it's in the public interest to not have that happen. And so KPMG is regulated by the federal government to, you know, be honest and independent about this sort of thing. And about 10 years ago, they got into sort of the advisory business, and so that's technically the arm under which we fall. There's something like 28,000 people who work for KPMG in the US, and there's 200 of us who are in what's called internally the Lighthouse, which is the Data and Analytics Center of Excellence. So that's kind of this is like business lingo that I had to learn. But it's basically the group within KPMG which partners with other groups in the firm when they need someone who can do natural language processing or understands the intricacies of, you know, statistical modeling and that sort of thing. And so because KPMG is so big, we get a chance. Oh, this is kind of the resolution isn't that great. We get a chance to do a lot of different stuff. So you know, this is just like a laundry list of things that get done. And so, you know, this is ranged from, so I've had a colleague work on taking like, you know, the undergrads among us are probably young enough to remember when they took like the PSATs in high school and they started getting loads and loads of mail from colleges, you know, trying to say, come here, come to Northwestern or whatever. We've had a project that works on taking publicly available data along those lines and trying to figure out, you know, which students colleges should target to try and recruit, you know, who's most likely to matriculate. Natural language processing is where I've done the bulk of my work with KPMG. I had basically no experience other than speaking a language before starting. But the idea here, I'll talk about a couple of projects that we did there. There's a whole big effort, like companies are producing more and more data, and that's why people like yourselves are in demand. And the idea is that if you can create a lot of data like astronomers do, astronomers are really good at making lots of data. So they think that you know what to do with it. So there's a whole component of helping companies figure out like what to do with their data. And so, you know, so that's sort of more classical advisory. And then there's some times where you may have heard of like the Dodd-Frank Act, which was passed in the aftermath of the 2008 financial crisis, that added a lot more restrictions on banks. In particular, this notion of stress testing to make sure that, you know, if something really bad happens, the bank won't need a bailout. That's almost entirely a statistical modeling exercise. And so what sort of catastrophes you come up with, how does that affect the volatility of their, you know, their balance sheet and that sort of thing, is something that we do quite a lot of as well. And because we're a consulting firm, this is another this isn't my slide, it was borrowed. One of the nice things, and the reason I picked a consulting firm is because I didn't know what I wanted to do. And so I wanted to go to a place where you could work on whatever technology that you wanted to work on. And so the idea here is that we're kind of tool agnostic. You can work on whatever gets the project done the best and the fastest. I mostly use kind of open source, big data stuff, Python, some Java, commodity libraries for NLP and that sort of thing. But this is like a laundry list of stuff that you can use here for KPMG. So, again, this is a borrowed slide, but the idea here is that If you've ever like called your utility company or your credit card company, you get on the phone with a person and they are like, "Why are you calling?" And this is all documented. Like every time, so I just called and canceled a credit card the other day. There is some note about my call in some database somewhere. And call centers are also really expensive for companies, and they're a constant source of frustration for customers. And so understanding how your call center is or isn't working is like actually a fairly compelling business need. And so for this client, they came in and they wanted to know just like, why are people calling us? We have, notes that are made, and then the person on the phone who's taking the notes will attempt to classify the message, but they wanted to get a feel for how well that was working. And so I can't actually, I can just read it. But this is a note here, and it's about, 7-8 lines long, and it says CCI, COCHK, ACCNT, BAL, and due date. And then the rest here is some date and time tagging, along with who entered the message and stuff like that. And so, how does that get classified? Well, so there's a couple of things you need to know. Like, one is CCI's abbreviation for customer called in. And so basically what this person wanted to do is to check their account balance and when the bill was due. And so, but along these steps here are the steps that our algorithm eventually used. And so the idea was to take this and somehow classify it in a vector, so that then you could feed it into a deep learning sort of algorithm that would take the vector that represents that particular call and map it onto one of these categories down here. So somewhere in here, it's like not wearing your glasses, but somewhere in here there's like a balance check kind of phone call. And some here, one of them here is like the bill is too high, or they want to enroll in automated billing or something like that, or various other reasons. And the blue bar is how they were classified originally by the people who were typing the notes, and the green bars were how the algorithm ended up hacking them. And so there's quite a discrepancy here. I forget which these are. Let's see if I can see on my screen. No. The thing that I've found, speaking again from a physicist perspective, is call center notes are actually, they're not black holes. They're not high energy physics or anything like that. So there's less motivation for me from a big picture perspective. But the actual project here, which is to figure out how to clean the notes, how to tokenize. By tokenize, I don't know if you're natural language processing, but break it up into individual entities. Rationalize the abbreviation from CCI to customer called, and then we still have a tokenized vector. You remove something called stop words, which are just like is and to that don't really affect the meaning of what you're trying to do. And then use keyword extraction provided by the client to help set the vector. And so it's an interesting computational problem. And it pays dividends for the client too. So, it's like kind of the best of both worlds. And you get to use cool things like deep learning and all of that. And so this is just, there's a whole, I don't know if you're familiar with it, but like word2vec and deep learning framework that sort of does this. And so we didn't quite go that route, but it's definitely inspired by that route in this particular instance. Oops, I'm skipping a telecom. So yeah, that was this particular project. Are there any questions on that one?
Chris, how'd you get truth data in this? So, I mean, the core.
So,
yeah, how'd you get
so I guess the question is, how did you sort of get the representative sample? And so the trick about these projects is they're not my projects, but so the number on the y-axis here is something on the order of like 80,000. So this is, they started with a small sample that was sort of human verified with the client. And so I guess that brings up another point is, I actually drew this project. It's a nice segue, so thank you. So this is a project that related to the Dodd-Frank Act and what's called the Volcker Rule, which is whether or not certain securities are, covered under the restrictions put into place by that piece of legislation. And the idea is that if you're a rich person, like a financial institution can sell you whatever. Like they figure if you buy something, you're rich, so it's on you. But if you own like less than $2 million or something, they're required to, what they can sell you and how they sell it is much more restricted so that they're not taking advantage of you. And so they offer, there's a multitude of instruments that you can be offered. And what they would want to know is whether or not they're covered or not covered under different parts of the statute. And so, so the input data is both the statutes, which are complex and there's many different layers of rules, and also the text of the actual instrument itself, which can be hundreds of pages of how this financial instrument actually works. And so, normally the way these things are classified is someone who's an expert in securities law comes through and reads them. But that's even if you use sort of like someone who's just fresh out of law school, that they can only read so fast, and these things are very expensive to do that way. And so you could be, there could be thousands of these instruments that are available for purchase in various different combinations and permutations. And so the solution here then was to take an NLP pipeline that looks for certain phrases that are then sort of referenced against the rules that are put into like the statute, which are then programmed into looking for these certain rules. And it's sort of a very it's like the old game, the pachinko game on Price is Right, where things eventually filter through. And then in the end, there's two big buckets, which is covered and not covered. And so it looks for certain combinations of phrases using a rules language that we design. And the point of this particular talk was that you can be an expert in natural language processing, which is taking a written sentence and pulling out what the subject is and doing part of speech tagging and looking for named entities and that sort of thing. But without the manual review feedback, you're basically doomed to failure. And so being able to sort of both, in this case, this is drawn from a document that's used to sell this service to potential clients. But the idea is that you want someone who is a subject matter expert to help you to write this pipeline. And while that may seem obvious, it seems, phrased that way, it seems to be less obvious once you look at things that are happening. And so, so again, the idea is, looking for features within the document. You have this derived regulatory rule set and the semantics that go with it, and then you feed it into this sort of, complicated pachinko machine, and eventually out, what comes out is covered or not covered. And so there's a similar set of projects that takes, a business is subject to contracts with other businesses, potentially with the government, potentially with clients, potentially with its workers, and new contracts are coming in all the time, and it's in the interest of the business to be compliant with its contracts. And so a similar project is taking those contracts and looking for variances. Some of the contracts contain the same boilerplate language, but where is this contract different? How do we direct our counsel to look at certain things? And so that's an example project that's very similar to this. It's based on a custom designed rules language and rule evaluation methodology that works until so it identifies which chunks of the contract are actually in type of
Chris, I
scrutiny.
just want to interrupt
Yep.
for just a second. So we are drawing close to 5 o'clock. We have
Okay.
5 minutes left on our promised time. So if you could wrap up real quick
Sure.
so that people who have to leave at 5 can leave. But then, everybody's welcome to stay for Q&A. We're here until 6 if you want. Chris, I guess, depending on his availability.
I can stay until 6.
It's a great, it's a great talk, but unfortunately because of the pizza delay and the time constraint, we have to.
So this is the takeaway of that. You can see that the machine is actually very slow until we figure out how to make it work. And then eventually the machine wins hands down. And so the first couple of iterations, the machine was really bad, quite low accuracy, but the feedback and refinement part was essential. So, come talk to me if you're interested in working for KPMG. Arthur is a former physicist like myself, PhD. He did neutrinos. Hung Fei is a PhD computer scientist. Linsha is a PhD in quantitative economics. Evan has his MBA from Stanford, so there's quite a wide variety of people who work here. Civil engineers, industrial engineers, electrical engineers, physicists, mathematicians, operations research people. And we're spread all over the country. We have a big office here in Chicago, but if you wanted to move somewhere like Denver, which is great, that's where I live, Atlanta, Orange County, or New York, we have locations a lot of places. Yeah, this is the timeline. So we're here doing recruiting for campus. So if you're enrolled in a degree program and graduating between now and June, this would be the cycle for you. So we're having a meet and greet tomorrow night, but we're also doing coffee chats so you can get someone's perspective on this other than me. On Friday at the Panera. I'm trying to figure out how you guys can sign up for it, but we'll see. And that's that. So thank you.